Now this circuit looks quite complicated, but if you just peep into it a little bit in detail, it is a very simple circuit actually. To discuss about the circuit, if you see here, there is a transformer here named as T1. This is the primary side of the transformer, as we are giving an input signal from this end. So the input signal here is nothing but the modulating signal. And this is the secondary of the transformer. To the secondary, if you observe this side, we have connected VCC. This is nothing but the DC voltage which we are using to bias the particular transistor here. Biasing is nothing but giving some suitable voltage to the transistor so that the transistor is ready for operation. We will deal about biasing in detail in the later chapters. So coming to the next transformer, it is T2. In T2, observe, this is the primary side where it is named as L. So this is the primary side and this is the secondary side, and from the secondary side we are tapping the output signal. Now coming to this particular component, you have already studied, it is the transistor. Here the resistors RB and RE are also used for the biasing purpose. About the topic of biasing, we will be discussing much in detail at a later stage. This circuit, what you see here, it is nothing but a class C amplifier circuit. And how does this class C amplifier circuit work? About that in detail we will be discussing in the chapter of amplifiers. As of now, I will just give you the brief required knowledge of working. Okay, so now here in this particular transistor, for it to operate, first of all, we need to apply some voltage. Okay, and that voltage that we are applying to the circuit so that it works according to our needs is called as biasing. So biasing is nothing but application of some suitable voltage to this particular circuit so that the circuit will work as I want it. Okay. Now to this circuit, the input signal that is applied is nothing but the carrier signal. Now when this carrier signal is applied to this particular class C amplifier, how it works is, observe this particular diagram. This is the first cycle here. So this is the beginning of the cycle. This is the positive peak, negative, sorry, the 180-degree completion. That is nothing but completion of the positive half cycle. This is the negative peak. And then here is the completion of the first cycle. So for this one complete cycle, you see that at the output of the class C amplifier, only the positive peak is observed. If you consider the second cycle, again for the complete cycle, you see that only the positive peak is present. Like this, for all the cycles, whatever we are applying at the input end, only their positive peaks will be observed at the output end. So the signal here, you see that it is not continuous. It is there for some time and then not there for some duration. Again, you can see the signal for some time, then again the signal is not seen for some duration of time. So this type of discontinuous signals, you call it as spurts of signal. S-P-U-R-T-S, spurts of signal. And these spurts are seen at the collector end, that is at this point. Okay, so this is how the class C amplifier works in brief. And these spurts, whatever is seen here, it is later applied to this tank circuit. You can see the L and the C parallel combination here. This is nothing but the tank circuit. And what this tank circuit does is, whatever the spurt signals are there here, they are not continuous sine waves, right? It is not a complete signal. So these spurts are converted into complete sine wave by this tank circuit. And at the primary end, you get the signal that is coupled to the secondary here. And then the output is tapped here. So having this basic introduction about the circuit, now let us see how the transistor collector modulator circuit will work. Now let me consider an initial condition wherein the modulating signal is not applied. That means the voltage here is nothing but equal to 0 volts. So this 0 volt signal gets coupled onto here. It is also nothing but equal to 0 volt. But then observe there is a DC voltage here which we have named as VCC. So that means if I calculate the total voltage at this particular point, at this point where the cursor is pointing. So the total voltage at this point will be nothing but the sum of this DC component and the AC component. And as of now, the AC component is nothing but equal to 0. So according to this equation, I will have the total voltage at this point as equal to VCC plus 0, which is nothing but equal to VCC. This VCC voltage, which is observed at the collector end, this is applied to this circuit as the biasing voltage. So for this given biasing voltage, the circuit will generate these spurts. And until this biasing voltage is constant, the amplitude of these spurts will be constant. In case if the biasing voltage here is increased, that time the amplitude of the spurt increases. And in case if the biasing voltage here decreases, then the amplitude of the spurt here automatically decreases. So having this basic idea, let us get into the working of this particular circuit. Now, what I will do is I will apply this modulating signal. So initially here at the beginning of the signal, the amplitude is nothing but equal to 0 volt. So that means the condition is very much similar to the previous case, wherein the 0 volt is getting coupled from the primary to the secondary. So the total voltage here will be this 0 plus VCC equal to VCC. So for this VCC voltage at the collector end, the transistor is biased at a particular level, and because of that biasing, the spurts are generated at one particular amplitude. So this is the beginning of the AM wave, where you can see that the particular signal is at a constant amplitude. Now, what I will do is I will just consider this particular AC signal to be of a swing of 505 volt. That means the positive peak is at 5 volts. This is the 0 volt time axis line, and this negative peak is at minus 5 volt. Okay, so the positive peak, I repeat again, is at plus 5 volt. The negative peak is at minus 5 volt. Now let me take some intermediate value, wherein say the voltage here is equal to nothing but 1 volt. So if the AC signal here is at 1 volt, then that 1 volt signal is seen at the primary. It is coupled to the secondary. So if I now measure the total voltage here is VCC plus 1 volt. Okay, so now you can see that when compared to the previous condition, the current biasing is slightly increased. So because of that, the spurt of the particular wave generated here will also be of slightly greater amplitude. As a result of this, what happens is when this spurt is applied to this tank circuit, the tank circuit will generate a sine wave which is also slightly greater in amplitude when compared to the previous condition. You can observe it here, the amplitude is slightly increasing. Now, as I further increase the modulating signal, say for example, I come to a situation wherein the amplitude here is 3 volts. So now 3 volt is seen at the primary coupled to the secondary. So the total voltage here will be 3 volts plus VCC or VCC plus 3 volts. So now if you observe the biasing given to the transistor, it is now even more increased when compared to the previous condition. So that means the amplitude of the spurt here is also further increased, and the sine wave generated from this particular tank circuit is also now increased. So you can see here the amplitude is slowly increasing. Once I reach this positive peak we assumed it to be at 5 volts. So now the total voltage at the secondary is nothing but equal to 5 volt. So the voltage at this point is VCC plus 5 volts, which is nothing but the biasing supply at the collector end of the transistor. So now, when compared to all the previous conditions of biasing, the current biasing voltage is at the maximum. It is at VCC plus 5 volts. So, for this maximum biasing voltage, the collector end will have the highest amplitude spurts. And because of that, the sine wave generated here will also have highest amplitude. So, we reach to this positive peak. Now, as I travel further here, say for example, I come to the 3 volt point again. So that means the voltage here is 3 volt. So that means the voltage here, AC voltage is 3 volt. So the total voltage at this point is nothing but equal to VCC plus 3 volt. So now you can see that when compared to the previous level of biasing, the current biasing is slightly reduced. When the previous condition we discussed it at VCC plus 5 volts. The current condition is VCC plus 3 volts. So that means the amplitude of the spurt is now slightly reduced. And because of that, the amplitude of the sine wave generated here is also slightly reduced. So it will be this region of the envelope at this point. As we further come down to the end of the positive half cycle, the amplitude here is 0 volts. So that means, can you guess the biasing voltage here now? It is equal to VCC. So VCC plus 0, that is nothing but VCC. So now here the biasing of the transistor will be as it was at the beginning of the circuit. Clear? Now when I proceed further here, this, let me come to the negative peak here. So the voltage here is now the voltage here is now minus 5 volts. So that minus 5 volt of AC signal coupled to the secondary here. So the total voltage here now will be VCC minus 5 volts. So that means, observe, the transistor is at its minimum biasing voltage now. So that means the spurt generated here is at its minimum now. And because of that, the sine wave generated by the LC tank circuit is also at its minimum. So that is shown here. This is the point where the amplitude of the signal is at its minimum. Now say for example, from this minus 5 volt, we will go to a point somewhere here which say is measuring minus 3 volts. Okay. So now minus 3 volt AC signal here coupled to this side. So that means here the total voltage now will be VCC minus 3 volts. So that means when compared to the previous value of biasing, which was VCC minus 5 volts, now it is VCC minus 3 volts. That's it. So observe, the biasing of the transistor is now increased by 2 volts. So that means the spurt here, it is having a greater amplitude. Because of that, the sine wave is having a greater amplitude. So you can see here from this negative, now we come to this region of output wherein the amplitude is slightly increasing. As we further go ahead, we come to 0 volt and then we come to the positive 5 volt. And accordingly here, the amplitude is continuously increasing, and this is the point wherein the complete positive 5 volt is observed. So like this, the signal here, as its amplitude varies, you can see that the output signal's amplitude is also varying. So with this technique, we generate a AM wave. The notes for that is given here. You can just make a note of it. This is the second part of it. Now we will move on to the advantages of this particular circuit. The advantages are, the collector efficiency is very high. Usually this class C amplifier has a high efficiency. Second one is the power output is very high. The modulation is linear. That means it is directly proportional. Coming to the disadvantages, the first main disadvantage is the modulating power required is very high, and the other disadvantage is, due to the collector saturation, 100% modulation is not always possible or not possible at all. With this, we come to an end of today's video session, students. See you soon with the next video wherein we will be discussing about the types of AM and the AM transmitter. Till then, take care. Bye-bye.